Thank you very much, Niels. Thank you, everybody. Yes, as Niels highlights there, you know, we've geologists have for many years analyzed strain histories within rocks. We get a nice finite strain. We understand something about the history of deformation, whereas the topography that overlies those deforming rocks has been much less understood and appreciated in terms of the dynamics between the surface processes and the tectonics, and that's what I'm hoping to explore a bit in this presentation. Now, in order to understand highly strained topography, I'll come back to this illustration in a minute, it's interesting just to consider what an unstrained topography looks like. So there have been a number of studies on small soil-mantled hill slopes showing the remarkable periodicity of catchments, the internal dimensions and aspect ratio of these catchments over a couple of orders of magnitude, and that this periodicity seems to scale up. We understand something about the coupling between advection and incision of rivers to form this sort of process, and this seems to scale up to the scale of large mountain catchments, where this plot by Niels many years ago illustrates the dominance of this 2-to-1 ratio of outlet spacing, half width of catchments of mountain belts and the length of the catchments to the outlet spacing. And so you see this sort of frequency plot with this peak at around 2, showing you get these slightly elongate catchments. But as he noticed, and many other people have highlighted since, is that the Himalaya are somewhat different. They've always seemed a bit anomalous, and it's been explained in a number of ways, but the catchments seem to have a more equant form. Their length to width ratios seem very similar, nearer 1. So understanding this, you might say, well, surely the size of the Himalaya and the amount of strain across the Himalaya may have something to do with this. We know that in a number of mountains that faulting will dislocate catchments, it will force drainage capture, it will distribute outlet spacings into different positions at the front of mountain ranges, so you'd expect faulting to play some role. And if you look on a very large scale, this paper by Halle and Molnar suggested that the very large rivers of the Mekong and the Salween were actually represent passive strain markers on the landscape, and they record extreme deformation at the corner of the Himalayas. So you may expect, if these sort of processes are active, that the anomaly of the Himalayas may be related in some way to this. So in order to analyze this a bit better, we need to understand what counters the tectonic forcing. And this is very nicely illustrated by Sean's paper recently, showing the way in which the dynamism of drainage divides, the way in which catchments are very dynamic, and we can explore the nature of the migration of drainage divides. These are catchments within Taiwan, showing the arrows illustrating the migration direction of these catchments. And this is mapped out by understanding the nature of the river systems and the erosion of the river systems as approximated by a stream power model, which is widely used and models erosion as a power law function of slope and channel slope and upstream area. So if we take that approximation of the way in which rivers behave, we can make some further predictions which might help us consider large-scale mountain ranges. So if we think of a stream power model, if we just start, first of all, with a simple, undeformed series of catchments, there's catchments A and B, this would be their long profiles here, this would be a ridge profile, then the length-width ratio we'd expect, as Niels highlighted, to be around 2. But if we consider a fault system running through a series of catchments of variable size, we would expect the response of a river to displacement by a fault in a stream power world or model which has been well constrained is the migration, upstream migration of a kinetic wave or a nick point, over steep and reach up the catchment. And so this has some dependency, the ability to recover any deformation, so the red arrows represent the shortening, the ability to recover that deformation will be a function of the size of the upstream area that is being readjusted. So you may say, well, if we have a series of faults, we may get smaller catchments which are fully recover any shortening, and in order to fully recover that shortening, they have to erode the equivalent material that's been vertically displaced, i.e. the throw on the fault. So for a catchment to recover that deformation, the throw rate, the erosion rate has to be greater than the throw rate to fully recover it. But if we say that's scale dependent and we look at this plot, we might suggest that actually length-width ratios may change as we get into larger catchments. And there are other reasons that this might happen. The likelihood of being intersected by a fault is increased, obviously, if you've got a larger catchment. So, sort of geometry, so we went, first of all, to test that in the Himalayas. And so here we have the arc of the Himalayas. There's the main drainage divide between material that's draining into Tibet. This is the suture. The red dashed line there is the MCT, and this is the main frontal thrust here. These are GPS rates of shortening between Tibet and stable India. And we can see here what we've done is sampled all the catchments that drained into the front of the Himalaya, which has been done by many others, but we've also sampled the catchments which drain into the two other first-order lineaments in the mountain range, the Indus River and the Tsangpo. And so we've separated this into the catchments in the lee of the Himalaya and those into the front. And when we plot those catchments up, each one of them we plot up for the length to width dimensions, and we see a plot like this. So there's the aspect ratio. There's an aspect ratio of 2. We can see, as is known, this is a running mean with an error on the mean for the front of the Himalaya in purple and the lee in the crosses in blue. And you can see that there is this scale dependence. As you increase catchment area, we see a much higher proportion of catchments which appear to be wide relative to their length. They appear to have some degree of elongation parallel to the mountain range. So that does seem to go along with the support that there is some scale dependence on the ability to recover strain, as I suggested at the beginning in that cartoon. If we look further at the data, we can see that's the same plot, aspect ratio against catchment area. Here we've just plotted catchment area against catchment relief, just to show that these catchments in the front of the Himalaya have the much greater relief. And you might associate relief as a proxy for the age of these catchments. I think that is also a parameter in here, is the actual age of the catchment that might have accumulated strain through time. If we look at the map, the distribution here, these are the values of the aspect ratio with more elongate values parallel to the mountain range in red, more elongate perpendicular to the mountain range in blue. You can see the colors are dominated by the reds because these are the big catchments which are elongating parallel with the range. The smaller blue data would all be along the front ranges and along these two main valleys. So the initial interpretation here is that catchment shape is scale dependent because erosional recovery from faulting is area dependent. Larger catchments are more likely to intersect faults, and larger catchments potentially record a greater duration of shortening, i.e. they're older. This has implications. If we start life as a small mountain range, such as Taiwan, we may expect to see this regular spacing, and this has implications for the sediment delivery and the water delivery to the surrounding fallen basins. And as that system grows, if we expand an origin of that sort, we may expect to see more differentiation of catchment size and catchment form, and more differentiation of discharge down into the mountain front as the system expands. So that's all very well, but there are a number of people who work in the Himalayas who will tell me that, well, actually, look, here's the modern strain tensor and the shortening rate across the Himalayas, but this is not a record of the long-term history of deformation. And as Peter has very nicely presented, that most of the shortening during Holocene times has been taken up along the mountain front here at the main frontal thrust. And in fact, there's very little evidence of strain or shortening going on at the present in this area. And if you go with the simple model of this part of the Himalaya being, rather than internally thickened, being uplifted over a mid-crustal ramp, then in fact there's no need for shortening in here, so how come you're suggesting that there is deformation of these catchments, which is a fair argument. So we need to go into this Lee region of the Himalaya and explore exactly this process. So what we're going to do is take one catchment and we're going to explore the relationship between shortening rates, if there are any, and erosion rates, and see whether or not we would predict ongoing shortening within a system like this. So we're going to go into the Indus Valley here. This is the Indus Valley running along there. This is the Ladakh batholith, so this is part of the Gangdesi Arc, and this is a fold and thrust belt here involving the same age molasse succession that we just heard from Barbara, except this material here is much more deformed, and the great counter thrust, as was described here, separates the Ladakh batholith from the deforming molasse. So we're going to look, this is one of the main valleys. This is the main Indus Valley that flows along effectively the back of the active Himalaya. So if we go into that area, into that particular part of the valley, this is the topography. This is the Indus running through here. This is a river called the Zanskar running draining into it. The town of Leh, where you fly into. These are deformed molasse sediments. This is the Ladakh granodiorite. So if we look at a view from here, just looking towards this deformation front, we see here, these are the Himalaya behind. We're looking south. That would be the thrust front of the deformed Indus molasse. Back thrusting and northward thrusting onto the granite here, and this is the Indus Valley. If we go into this region here at the thrust front, we can see that it's the river as it cuts here through this gorge. There are a series of terraces. There's a nice high terrace here, which is an alluvial terrace. Within that alluvial succession, there's a very pale bed, which I'll look at in a minute, and we've got other terraces lower down in the succession. So we can date these terraces, and of course terraces are very valuable for trying to assess rates of recent quaternary shortening, if there are any at all. So going into this region, we're now looking south. This is the Indus molasse, and that was that pale bed just within that terrace succession, and this is a thrust here of the tertiary molasse. These are folded Pleistocene gravels. This is a big mass flow breccia, and these are lake sediments above it. And if I just simplify that, so here's the thrust would be in there. This is a line drawing of this photograph, this panorama, and this is a sort of schematic cartoon of what we're actually seeing. So we're seeing thrusting over these deformed Pleistocene gravels. We can date the gravels. And I didn't, oh, there they are. Yes, they're dated. We've got OSL dates, and these are concordant with lots of other OSL dates in the region. And of course, so we're deforming these fluvial gravels. We're then associated with that deformation. We seem to be putting big debris flow over the top, and then that's damming the valley, and we're getting these lovely lacustrine sediments as you block the whole valley after that, and then you get alluviation over the top of that. But based on this, we can calculate the amount of shortening here, 9.8 meters since about 38 million years, 38,000 years. We can also map out the terrace across the valley, look at the displacement there. So this is a cross-section across the valley. The high terrace D that we were looking at here is displaced vertically by 17 meters, so we can look at that vertical displacement. We can calculate the shortening based on the dip of that thrust. And so we get a minimum shortening rate of about 0.6 meters a year. Very slow, considering the whole convergence is 20 millimeters a year, but there is shortening in this part of the Himalaya during the Quaternary, and this would be associated with a vertical displacement of 0.45 millimeters per year. So if you want to maintain that shortening, you need an erosion rate that's significantly slower than 0.45 millimeters per year. If not, then it implies that that system, that catchment is narrowing, the topography is actively narrowing. So if we now look into that, that's where that thrust fault, where the Quaternary sediments were recorded. This is a lateral tracing of that thrust fault. This is the valley again. We can try to evaluate the lateral activity of this particular structure then by looking at the nature of the rivers. And this is this is the same methodology that Sean used in the previous paper illustrated. So this is looking at effectively the steepness of rivers normalized for upstream area. And what you see in these sort of regions is that the steepness of these rivers looks highly variable, and this is largely because they're heavily glaciated in their upper reaches. So really it's very difficult to look at the steepness of rivers and associate that with tectonic activity when you've got glaciated systems. So we removed the glaciated catchments and just looked at the steepness of the unglaciated catchments where they were behaving in a very well-organized manner. So we have a series of catchments to the south, a series of catchments to the north, and we have a thrust fault between them. We're going to see if it's active right the way along the mountain front. This is a plot showing so there's the batholith to the north, the molasse to the south. This would be where the river, the Indus River, is flowing. So these rivers, and what we're plotting here there's no longitudinal profile. These are values of the effective steepness of those catchments. What you can see is on the batholith, they're relatively stable, so the colors match opposing on the opposite sides of the valley. You see over here, we've got much more irregular values of the steepness, this chi parameter, and we would interpret these. There's a structure that's been mapped internally within the system here, and this would represent the deformation front. So we think we can map the activity of that structure right the way along the Indus Valley. So we've got a fault active along the whole front of the range and internally. So let's now look at we know the rate of that. Let's now look at the erosion rates. So the erosion rates on a similar time scale are best approximated by detrital beryllium-10. So these are, so these are, given the erosion rates that they're yielding here, these are in millimeters per year. We can see slightly faster rates off the deformed molasse, 0.07, 0.08, quite consistent, and then slower rates coming off the batholith. And these, given those erosion rates, are averaging over time periods about 10 to 20,000 years. This compares, interestingly, with the longer-term exhumation histories derived from thermochronology. Easiest ones to compare are simply the epitite fission track ages, which are younger, between 14 and 11 in the molasse, and then much more towards 30 in the batholith. We're looking at a significantly faster erosion rate when averaged over a longer time period. So it appears that the modern erosion rate is less than the longer time scale when you average over several millions of years. But nevertheless, that asymmetry is still there. So what we see, that would be the Indus Valley. These are the batholith sediments. Those are the batholith profiles, the molasse rivers. This is the batholith erosion rates, much slower, the molasse erosion rates. And just to put on from AFT, just to show you that they are, again, that difference is there, but the overall values are higher. So flow rates are 5 to 10 times faster than erosion rates, which suggests that in this area, relief is growing and the valleys are narrowing. How much time have I got, Niels? I've got some, great. Oh, well, I'm finished. Great. So I can relax over these conclusions and look for lots of discussion. So I think the conclusions are that catchment strain appears to be scale dependent, and I think this has interesting implications for the progressive evolution of mountain ranges and the way in which catchments evolve. And so this sort of cartoon illustrates progressive deformation, and this represents the scale dependency. For strain to be recorded, fault throw rate needs to be greater than the erosion rate. And even in the lee of the Himalaya here, where deformation rates are very slow, but the erosion rates are even more slow, meaning that you can still narrow at rates of about 0.6 millimeters per year, i.e. 6 meters per 1,000 years, 6 kilometers a million years. So it's those sort of rates we're looking at. Slow, but it's happening. And that's all I've got to say. Thank you.
Thank you. I like the Gordon rule, so we'll stick with that. We'll start with questions from young scientists defined as within 7 years of PhD or under the and/or under the age of 5, according to the EU rules. I think it should be under 60.
Wow.
Young scientists.
There's a couple up the back there.
It's 7.5. Is it allowed? But I have
Pass
2 children, so it's 3.
Can we see how difficult the question is and then decide?
Well, I have a question. It's why is that difference between the actual, the modern erosion rates?
Yeah.
Why are so much lower than the let's say the erosion rates since 12 million years ago? What would be the explanation?
Yeah, this is now a very arid landscape. So, there is very little evidence of active erosion except for extreme events.
But it was arid since a long time ago, apparently.
Well, no, 20 million years ago, as we've just heard, we were having, in those molasses, we were having crocodiles, and I've got tropical leaves, etc. So somewhere between 20 and modern, we appear to have uplifted, absolutely, and we appear to have dried significantly. So I would imagine it's a combination, and as you propagate and develop the high Himalayas, so you're more into the rain shadow, so potentially we are, but I suppose that's earlier, but I think, we're looking at a drying of the area.
Yeah, I know that, but isn't it again possible that maybe because we are within this interglacier, then you have a very different erosional rates than within the glacial times?
The glaciations up here are out of sync with the normal sort of mountain glaciations globally. So the last glacial maximum here was about 100,000 years ago. So this has been within an interglacial for a long period of time. You don't see much evidence of huge amount. The sediment flux is primarily incising into moraine. The sediment yield is in the granitic system is coming from moraine. In the south, it's hill slope. I don't think there's any great evidence that glacial interglacial cyclicity is playing a major role here.
When you compare the gradients of the batholith versus with respect to the morass, how much lithological control would you expect also on that, because it's very different, no?
Yeah. The concavity of these two systems is identical. So they appear to be behaving in a similar way. But there could be a variance as a function of lithology, but they wouldn't show that degree of variability in the chi parameter. So it's jumping around as the rivers are steepening downstream. So if it was that, and it was simply that, you might just get a uniform signal, but it's not.
You attribute the anomalous form of the catchments to deformation or to strain only. Whereas in particular, I think for the frontal Himalayan catchments, there's quite a lot of evidence that this is actually capture of adjacent drainages. So, how could you discriminate between that, and how would it change your conclusions?
There's a good point to make. So, there are those who would argue that and justifiably that there is this problem of deflection and capture of catchments at the front of the range. You also get, there's an inheritance feature in here. You get elongation of some river networks parallel to lithological boundaries in some place, and zones of differential uplift. So there are other reasons, clearly, why you might get this signal. That doesn't explain, one, why the signal is carried right the way across the Himalaya, into the lee of the Himalaya and the front. And it doesn't explain why the Himalaya are relatively anomalous compared to other mountain ranges. So that's what I'm looking for. And those processes are there in most mountain ranges, whereas we're looking for something additional in the biggest range of them all.
Two halves to that same discussion, or two questions to that same discussion, I guess. Yes, this is different from other mountain ranges. Other mountain ranges have shortening and strain. Why is the Himalaya special in this case?
It's bigger.
And that's the other half of my question, which is why I don't understand the scale dependence argument. Strain is certainly not scale dependence. What is it about the catchments that somehow make them scale dependent? I just don't know what process does that.
You've got two catchments next to each other, cut by, faulting is discrete across a mountain range. You've got two catchments cut by the same structure, one small one its ability to readjust to that strain is greater than over a given time scale than the larger one. So the larger one will be in a transient state by the time, let's say, the next shortening event happens.
But you're presuming that a shortening event is somehow a transient, then it disappears, whereas if you have prolonged uplift of a fault, then you're adjusting to that new uplift condition, and then the perturbed state is in fact the strange state.
Yeah. No, I take that. So it's not as simple as just one event and a response. It's just an easier way to explain it. But when you integrate that over time, if the bulk strain rate or the throw on the structures as a result of the shortening on that fault is greater than the ability to remove that by erosion, to make it simple, then you have to have shortening across that structure. I agree that as you shorten, you narrow and you steepen, so there's a positive feedback, so you will get more erosion rate, so it can't carry on, which makes me wonder, when you look at the Mekong and the Salween, so Halle and Molnar would argue that really is complete, you strain that to such an extreme. And maybe I wonder to what extent that's associated with rotation of the main channel system, that when you really rotated the main channel, it's difficult to fire off the signal, the geomorphic signal, into the little tributaries laterally, as a few people have shown for, like Cam-Mobus for some of these rivers. Yeah? I mean, what's the other argument for how you get scale dependence?
Can we discuss?
Yeah. I'm genuinely interested. Is why do you get a scale dependence like that? And this is my simplest.
Why do you think it's scale dependent, though?
Well, you see it.
Question whether that's actually, in a short-term transient, yes, but any river will eventually re-equilibrate with its uplift and strain conditions. So, and it could be just, it might be that it is simply the time to re-equilibrate is just much longer. And, so exactly. Things like the Mekong might simply require another 100 million years before it re-equilibrates again.
Yeah, and if your shortening rate is faster, you're going to record shortening.
Well, it's not so much if it's faster, it's if it's steady or not. If it's steady, then you will reach some new equilibrium, right?
But you still have to explain this.
Yeah, it's complicated. Yeah, it's, in a way, I think you're presuming something that may not be true. It may not be true that, Jovius may have been wrong in '96, right? That there may not be a global aspect ratio under tectonic conditions, right? It could be under non-tectonic conditions you do. But if you're shortening and uplifting an area, maybe it goes to 1. You just have to have enough time.
Yeah, so we're both wrong.
Because I'm partly responsible for that, let me try to phrase a question in this debate. You propose that deviations from that aspect ratio of around 2 arise. That deviations from this aspect ratio of around 2 arise when tectonic straining exceeds the capacity of the geomorphic system to keep up. So erosion rates are slow with respect to tectonic rates.
Yeah.
Can you translate this into a more general notion that catchments worldwide in active origins with an aspect ratio that isn't around 2 indicate the tectonic growth of that mountain system?
I didn't catch the latter part. What was can you just repeat that? What you argue is that for these catchments that don't have an ideal aspect ratio, the tectonic rates exceed the geomorphic rates, which means that topography grows. Yeah. Okay. Yeah.
Yeah. There is an addition of mass.
Yes.
You can see that at the scale of the catchment, or you could see that at the scale of the mountain belt.
Yeah.
Can we therefore take the shape, the aspect ratio of catchments, and infer something about the mass balance of that mountain system?
Yeah, they should. According to this, you would expect there to be a transient period of topographic growth in the hanging wall as long as the strain is outpacing the erosion rate. So you would expect relief, and I think the tendency of these frontal rivers to show this increase in relief. Obviously, you can see it, you can visualize it. These are the big, steep, incised gorges. That's what's happening there. Whereas these systems at the back here seem to be stabilizing, and if anything, they've got relatively low relief. So, Actually, I think that's also, there's another story there. I think that's associated with the decoupling of the channel from the hill slopes, whereas these are much more coupled in where it's growing, where the topography is growing.
Are there questions? If not,